Hello and welcome to Lab 3, Black Hole. The purpose of Part 1 of this lab is to find the mass of the black hole by analyzing the motion of a star. The purpose of Part 2 in this lab is to use the mass of the black hole that we found in Part 1 to determine the initial velocity a spaceship must have to get close to the black hole without crashing on the planet or the black hole. All in all, this lab will show the effects of Newton's second law and its relationship with momentum. So a preview of results. The mass of the black hole that we found is 1.32952 times 10 to the 34 kilograms, and the initial velocity of the spaceship is the vector with an x-component negative 3.859 times 10 to the 7, and a y-component of 2.94 times 10 to the 6 meters per second. And to differentiate our systems versus surroundings, the system is the star and the surroundings is the black hole. So now to explain the fundamental physics principles. The first principle explored in this lab is Newton's second law, which states that the net force on a system is equal to the change in momentum divided by the change in time. Since the change in time is very small, we can use the derivative of momentum. From this, we can derive the parallel and perpendicular components of the net force in terms of momentum. Next is the gravitational force between the star and the black hole. By rearranging the equation for gravity, we can find the mass of the black hole in terms of momentum of the star. To find the mass of the black hole, we will use a computational model in GlowScript. This model will do so by finding the momentum of the star at various points throughout its orbit. For the code, we must input initial conditions of the star, shown in the code here. To calculate the mass of the black hole, we use the change in momentum over time times the distance between the star and the black hole squared, all divided by g times the mass of the star. So now shown is the star orbiting the black hole. Since the orbit is not a perfect circle, there is a different net force on the star at each point in its orbit. From this, we get the average mass from each calculated value, which comes out to 1.32952 times 10 to the 34 kilograms. Now in Part 2, we are using trial and error to find the initial velocity that will allow the spaceship to exit the orbit without crashing into the planet or the black hole. To do this, we will again be using GlowScript and need to input the mass of the velocity from Part 1 as well as more initial conditions shown, like initial planet velocity. Through trial and error, we will figure out the initial velocity and speed of the spaceship shown below, which has an x-component of negative 3.859 times 10 to the 7 and a y-component of 2.94 times 10 to the 6. For the rest of this code, we will be finding out the net external forces acting on our system using the equation for gravitation. Shown are the forces on the planet by the black hole and the ship, the forces on the ship by the black hole and by the planet, and the net forces for each. After all this trial and error, we finally get the initial velocity that allows the spaceship to leave the system, shown below. So some possible sources of error is the fact that we did use trial and error to find the initial velocity. So we could have gotten closer and been more precise if we had done more trials. Next, what does it mean? How does net force and its components differ from rate of change of momentum and its components? So mathematically, these two are the same, as net force is equal to change in momentum divided by change in time. However, change in momentum is much easier to calculate, since all you need to know is the change in velocity of the system, whereas to find net force, you must know every force being exerted on it. Lastly, what initial velocity would make the spaceship orbit the black hole? So to do this, we used more trial and error with the code, and we found the speeds below that would make the spaceship orbit. So in magenta, we see the spaceship's orbit, and the speed in the x component is negative 0.05 times 10 to the 7, and in the y component is 10.5 times 10 to the 6. Thank you.